Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will review statistics. Specifically, we'll look at box plots and scatter plots. So let's start with box plots. So box plots are displays like this. They're ways to display data. So box plots are always drawn like this. In fact, they're often called box and whisker plots because they have these whiskers and a box. The box always goes from Q1, first quartile, to Q3 with a line for the median, and then the whiskers go from the box to the maximum or to the minimum. So how would you calculate such a box plot? Well, let's say here we have a set of data. We actually have 9 scores. What we need to do is come up with these 5 numbers called the 5-number summary. So finding the minimum is actually really easy. It's just the lowest number, and Q4, the maximum, is just the highest number. So let's now look at finding the median. So the median is always the middle score or the average of the 2 middle scores. So whenever you have a situation like this with an odd number of scores, there will be one middle score. If you can't see what it is, you can sort of just cross off lowest, highest, second lowest, second highest until you get to the middle. The median here is 46. There are the same number of scores above it as there are below it. So when you have one middle score, what you do is cross it out, because to find the 2 quartiles Q1 and Q3, you need a lower half and an upper half, same number of scores in each. So Q1 is actually the median of the lower group. So here there are 4 scores. When you have an even number of scores, there will be 2 middle scores, and to find the median, you find halfway between. To find halfway between 2 numbers, you add them up and divide by 2. Here, Q1, the lower quartile, is 32. Similarly, the upper quartile is halfway between 59 and 71. If you don't know what that is off the top of your head, no worries, add them up and divide by 2. So here, Q3 is equal to 65. So this distance here from Q1 to Q3 is called the interquartile range. The interquartile range is just Q3 minus Q1. So 65 minus 32 is 33. The interquartile range is a bit more robust than the actual range because it's not susceptible to outliers. So in this data here, the actual range, 76 minus 19, is 57, but the interquartile range is 33. It tells you the range of the middle 50% of scores. So again, not susceptible to outliers. Because when we make a box plot, we're really dividing the data into quartiles, into quarters. So there should be around about close to 25% of scores between the minimum and Q1, 25% of scores between Q1 and the median, 25% between Q2 and Q3, and so on. So that helps us look at the data and decide, is it in the top 25% or bottom 25% or whatever. So after you've calculated the 5-number summary, so in this case, the 5-number summary would be minimum, then Q1, median Q2, Q3 65, and maximum 76. So after you've done that, you can easily convert it into a box plot. You just start the whisker here, box starts at Q1, line in the middle of the box for Q2, box ends at Q3, draw a whisker to the maximum. All right, let's now look at interpreting a box plot. So here I've drawn a box plot for you and given you the 5-number summary. So minimum, first quartile, median, upper quartile, Q3, and maximum. So how can we calculate the IQR? Well, that's actually really easy from a box plot. It's just Q3 minus Q1. So in this case, it's 80 minus 60. The IQR is just one number. That means the middle 50% of scores had a range of 20, between 60 and 80. So in this box plot, I want you to complete the sentence, 25% of students scored greater than what number? So remember, the box plot divides data into lots of 25%. So there are 25% in each of the 4 sections. Here, 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 and here. So 25% of students always score more than Q3. Q3 is the point such that there are 25, 50, 75% of scores below it and 25% above it. So in this question, 25% of students scored above 80. So you also need to be able to look at a box plot and determine its skewness. So you might want to think of what would this look like if a histogram was drawn. So you can see here that this represents 25% of scores, but it's a very small range. So if I was going to put this as a histogram, they would be high frequency scores. There's a lot of scores in a low range. As we go along here, again, small range. The range is a bit bigger here, 6, but it still represents 25% of the scores. So those scores are a little more spread out. And then if we were to go along here, you can see now the range is 14. 25% of scores were scored between these two, so they're a bit more spread out. You've still got the same number of scores, but they're more spread out, so it's going to look something like this. And same with this. Now we've got a range of 20. Still 25% of scores here. So they will make the histogram look a bit more like this. They'll be a lot more spread out, and so they'll have lower frequencies. So hopefully you remember from year 9 that this means that the data is positively skewed. Positively skewed data means scores are clustered towards the minimum. Negatively skewed means that they're clustered towards the maximum. If the data is not skewed, then it's symmetrical. So basically, wherever you see a low range of scores in the box plot, there will be a high frequency. So low range, high frequency. So if there's a high frequency of scores clustered at the minimum, it's positively skewed. A high frequency of scores clustered at the maximum would be negatively skewed. So just be careful. It sort of goes the opposite way that you'd expect. You might think positively skewed means lots of high scores. It doesn't. It means the opposite. So this box plot here is positively skewed. Just as an example, a negatively skewed box plot would look the opposite. So instead of having scores clustered at the minimum, it would have them clustered at the maximum. So you can see here, low range means high frequency. All right, now what we're going to do is come up with a set of 10 scores that could satisfy this data that has this 5-number summary. So to do that, I've drawn 10 boxes here. So firstly, it's obvious that the minimum is 56, so 56 would have to go there. The maximum is 100, it would have to go there. Now let's look at the median. The median is 66. So when you have 10 scores, you have the median in the middle, so there's 5 scores below, 5 scores above. So let's just make these two middle scores both 66. That means that the median of these scores will be 66. So now let's make sure that Q1 is 60. Well, Q1 is the median of the lower half. If there are 5 scores in the lower half, the third score will be the median because there are 2 above it, 2 below it. Similarly, this will be the Q3, it will be the median of the upper half. So I need to put an 80 there. So now all I need to do is fill in the rest of the boxes with any number that preserves order. So this has to be between 56 and 60. So why don't I just choose 58, choose a random number between 60 and 66, something like this. This will work. If you were to calculate the 5-number summary of these scores, it would be the same as up there. All right, let's now turn our attention to scatter plots. So whereas box plots display univariate data, scatter plots display bivariate data. So each of these points has 2 values. It has an x value and a y value, and they represent 2 variables. They can be whatever you want. X could be height and weight, it could be shoe size and IQ, whatever. It just needs to be 2 numerical variables, and they vary from person to person. So if you're looking at shoe size and IQ, each person has a different shoe size, so that's one variable, and they have a different IQ. So that is another variable. So scatter plots display bivariate data, and we're really looking at the relationship between the 2 variables. So the relationship can be no linear relationship, it can be a positive relationship or a negative relationship. So we're looking at whether or not the data lies in a line. So here, the points are kind of random. They don't really lie in a straight line. Then we say there's no linear relationship. There's no real trend. We can't really say what's happening to y as x changes. A positive relationship looks like this. As one variable increases, so the x-axis increases as we go to the right, so too the y variable is in general increasing. Negative is the opposite. Here we have as x is increasing as we go to the right, the y value is generally decreasing. One way you can look at it is draw a line through as much of the data points as possible. If it leans to the right, it has a positive gradient, so the relationship's positive. If it leans to the left, negative gradient means negative relationship. So when you're asked about the strength of a relationship, we're talking about how linear it is, how much it falls in a straight line. This is no linear relationship, but this one's a really strong positive relationship because the data is very close to falling in a straight line. Here, the relationship's negative, but it's not as strong. It doesn't quite lie in a straight line as much as here. In reality, very few things show a perfect linear relationship. They show a general trend. For example, for a positive relationship, we might look at height and weight. Generally, taller people weigh more. Doesn't mean that if you're taller, you absolutely weigh more. Just means in general, the taller you are, the more you weigh. So for something like negative, it might be something like, sales of hot chocolate and temperature. You would expect that as the temperature increases, the sales of hot chocolate decrease. Again, it's not a perfect relationship. It's not saying that if it's warmer, you absolutely will sell less hot chocolate. It's just a general trend. So these lines that I've drawn here are called the lines of best fit. So let's look more formally at how we calculate those. So to calculate the line of best fit from a scatter plot, what we want to do is draw a line such that it passes through at least two of the points, and there's the same number of points above and below the line. So if we have a scatter plot like this, you can see here that there are 8 data points in total. So we want a line that goes through 2 of the points, so there'll be 6 remaining. We want 3 points above and 3 points below the line. So a line of best fit might look like this line here. It goes through 2 of the data points, here, and there are 3 points above and 3 points below. Now we want the line to go through at least 2 points so we can calculate its equation. So you need 2 points to calculate the equation, and this is how you calculate the equation of a straight line. You just find the gradient first, and then you find b, which is the y-intercept of the line. So when you're given 2 points, to find the gradient, you use the 2-point formula, y2 minus y1 over x2 minus x1. Make sure you know it's y's on top for the gradient. And then to find b, you take your equation y equals mx plus b, you sub in m from the first step, and you sub in x and y from one of the points. So let's look at calculating the equation of this line of best fit. So it went through this point here, which is x value 165, y value 7, and the other point it went through was 178. So the gradient is y coordinate of second point minus y coordinate of first point divided by x coordinate of second point minus x coordinate of first point. So you can put that in your calculator if you want, you get 1/5. The gradient of this line is 1/5. Note that that 1/5 is positive. So the relationship between shoe size and height is positive. We expected that because the line's leaning to the right. You expect that because people who are generally taller have bigger feet. Again, not a perfect relationship. So after we found m, we're going to take our equation y equals mx plus b. We're going to substitute m for 1/5, which we just found. X and y get substituted from one of the points. Either one doesn't matter. I'll just choose this point, 178. So remember, x value is always first. So I'm going to substitute x for 170, and I'm going to substitute y for 8. We're now solving this equation for b. So 1/5 times 170, you can use your calculator, it's 34. So subtracting 34 from both sides, we get b is minus 26. So the equation of this line of best fit is y equals gradient times x plus b. Y equals 1 over 5x minus 26. Now let's look at using this equation. So the reason we might calculate the line of best fit is it allows us to make predictions. So this was our equation from the previous slide where x is height and y is shoe size. So we can use this equation based on our data to predict, say, a person's shoe size if they're 178 centimeters tall. All I need to do is substitute height for x. So here the shoe size would be y equals 1 over 5 times 178 minus 26. So putting that straight on our calculator, we get about 9.6. So we'd expect this person's shoe size to be about 9.6. Of course, shoe sizes are only in half sizes, so it'd be okay if you said it'll be about 9.5 or about 10. Either of those is acceptable. So that's just a prediction. Of course, it doesn't mean someone who's 178 centimeters tall will always have this shoe size. All right, let's now predict a person's height if their shoe size is 14. So we're taking our same equation again, but this time we're substituting y, shoe size, for 14. So 14, y equals 1 over 5x minus 26. So we add 26 to both sides, and then we undo timesing by a fifth by dividing by a fifth. We get x equals 200. So we expect from our data that if someone has a shoe size of 14, they will be about 200 centimeters tall. The line of best fit and knowing its equation allows us to make predictions. Of course, such predictions are not perfect. Doesn't mean someone with shoe size 14 will absolutely be 2 meters tall. Again, just a prediction. All right, thank you so much for tuning into this video. Best of luck studying for your tests, but you will ace it. This has been the luckiest maths teacher in the world. Have a great day.